Наша сессия, наверное.
Да, скорее всего, за этого.
Сессия. Я очень плохо смотрел, что трансляция началась.
Что еще раз?
В прошлый раз кто-то очень плохо смотрел, что трансляция
да,
началась.
я сейчас посмотрю, что посмотрю.
Как вы делаете?
Как посмотреть?
Да.
Ну на канал на ютубе зайти.
Ну вот в прошлый раз канал там был неправильный канал.
Ну да, ну сейчас вот есть. Сейчас загрузится, посмотрю, но есть название уже, что цепь Маркова.
Нет, я знаю, что она...
Не, есть.
То есть видно, да? Что...
Нет.
Ладно, в общем, запись. Запись будет, поэтому... Что... Сейчас еще подождем пару минут. Давайте, в любом случае нужно на английском, потому что... Okay, let's start. So, let me recall where we have finished where it was the last time. So we introduced the notion of the stationary distribution. This is such distribution pi that if initial distribution equals to pi, then the distribution of our Markov chain at arbitrary moment of time also equals to pi for arbitrary n. So in other words, it means that actually pi, this is just left eigenvector of the transition probability matrix, right? So we also formulated the notion of ergodic, or I call it mixing, right? Of mixing transition probability matrix. So transition probability matrix pi was called mixing. If there is such power S, positive, clearly it should be also should be natural, such that all elements of the matrix pi to the power S are strictly positive. Now let me introduce another two definitions. So this was the reminder about the last lecture. Another two definitions. So let me look which number of definition do we have now. So for the moment I have just recalled. This was corollary 18. Then it should be definition 19. This is definition of transition of mixing transition probability matrix. And now this definition 20, which says the following. A Markov chain psi 0, psi 1, etc. is called ergodic if it has a unique stationary measure, stationary distribution. Actually, sometimes I say stationary distribution, sometimes I say stationary measure. This is the same. Distribution. Let me call it pi. And moreover, for any initial conditions, for any initial distribution, its distribution of my Markov chain at time n converges to pi. In which sense? Well, we just okay. Let us say. In which sense we wish them to converge? If we are in finite dimension, right? If our Markov chain is finite, and now we mostly speak about finite Markov chains. I mean, the number of states is finite. Then it doesn't matter because all norms are equivalent in finite dimension space. If it is infinite, then well, let us say that it converges in L1. So that is distance L1 norm between the difference of the distribution at moment of time n and the stationary state pi goes to 0 when n goes to infinity. So I recall that the L1 norm, this is just the sum of absolute values of components of the vector we consider. Okay. Well, let me also write down what I mentioned. I just mentioned that stationary distribution sometimes I call it stationary measure. Also sometimes I will call it steady state. Also, one can call it invariant measure. Invariant measure. All these things are the same. Okay, are the same. All the first three definitions are completely correct. Invariant measure, I mean, it's also correct, but usually people use it in deterministic setting, more in dynamical systems than in stochastics. But in stochastics also people use this notion of invariant measure. Okay, so well, the next definition 21. Definition 21. A Markov chain psi 0, psi 1, etc. is called exponentially ergodic. Exponentially ergodic. So in the last definition it was just ergodic, and now it is exponentially ergodic. And now you can just guess that it is called exponentially ergodic if the convergence, okay, if it is ergodic, and the convergence is exponential. And the convergence is exponential. In which sense? In the following sense. There exists constants C, which is positive, constant lambda, which is in between 0 and 1, which is strictly less than 1, but which is strictly positive, such that for arbitrary initial distribution, we have that the L1 distance between the distribution at the moment of time n and the stationary distribution is less or equal than this constant times the constant lambda, which is between 0 and 1, times e to the power n. You see? So indeed, I just say that the convergence is exponential. Of course, you can rewrite it if you wish as here instead of c times lambda to the power n, you can write c e to the power what? Logarithm of lambda n. Wow. I mean, just often when one speaks about exponential convergence, often writes the estimate like that: e to the power some mu times n, right? mu time, what is this? Mu times n, right? And here it's actually the same, just you take mu equal to the logarithm of lambda, okay? Minus mu, because you wish to converge, right? And then mu will be the absolute value of the logarithm, because lambda is between 0 and 1. Okay? So this is just exponential convergence. Nice. Now, just pay attention that these definitions are not canonical, in the sense that this property of ergodicity in dynamical systems, it means similar thing, but which is weak. In dynamical systems, one usually says that the system is ergodic if the time average coincides with the space average. This is similar but stronger. Also, in stochastics, this property often is called mixing, not ergodicity. Sometimes it's called ergodicity, sometimes it's called mixing. Okay. This is then called exponential mixing, and the definition of the ergodic of the mixing transition probability matrix also is not canonical, in the sense that, I mean, the definition is canonical, but the word mixing here is not canonical. In many textbooks, it is called just ergodic, but I mean, in this case, we have too many words ergodic, and we have some problems that you can have ergodic Markov chain with transition probability matrix, which is not ergodic. And in order to avoid this confusion, we call this transition probability matrix mixing. Okay? So just pay attention to the terminology. It is not canonical. There is no canonical terminology in this area. So there are several notions which are similar, and like people use them as well. Okay. So theorem, and this is the main theorem of the course actually. Theorem 21, which is the ergodic theorem. So in Markov chains, usually people call ergodicity exactly this, but already in stochastic differential equations, which are like Markov processes with continuous time, usually this is called mixing. So this is indeed slightly confusing. Ergodic theorem. Assume that, okay, no, I formulate it slightly differently, in a slightly different way. Any homogeneous Markov chain. Homogeneous, it means, I recall that its transition probability matrix is independent from time. Any homogeneous Markov chain with finite number of states, and this is important. With finite number of states, so I will underline this. With finite number of states. I understand the finite number of states. It means that xi j can take finite number of values, right? You understand, right? Okay. So with finite number of states and mixing transition probability matrix is exponentially ergodic. Exponentially ergodic. So you see, once the transition probability matrix is mixing, the chain turns out to be exponentially ergodic. That is, once you take arbitrary initial condition, when time goes to infinity, you converge to the unique stationary measure, okay? Independently of the initial condition. And the rate of convergence is also independent from the initial conditions, you see? Because it's lambda and constant c, they're the same for every initial condition. This is actually a very, very strong theorem. Okay, moreover, the unique steady state, the stationary measure, phi satisfies the following inequality: just all its components are strictly positive. Okay. So there is no state with zero stationary probability. So what does it mean? It means the following: that if we have our frog with jumps between states, we have only finite number of states. Let us assume that the last one is state number L. It doesn't matter when it starts. It doesn't matter where it starts. It can start here, it can start here, it can start.
Думаю, Софи у нас включен, правда.
Да. Я тоже думал об этом. Спасибо. Во, ничего себе. We can start here with probability 1/2 and here with probability 1/2. It doesn't matter. Once you wait sufficiently long time, you can say that with probability approximately with probability pi3, it will be here, independently from its initial condition. So often people say that Markov chain forgets initial condition. Actually, analog of this theorem also holds for various Markov processes. For example, for processes which arise from stochastic differential equations under some natural conditions. And this is a very big activity to prove that some stochastic process is ergodic. For example, it is proven for Navier-Stokes equation. I mean, this is the famous equation which describes behavior of fluid, of viscous fluid, вязкой жидкости. So this is a famous equation because it's even, I mean, in dimension 3, it's even unknown if it has smooth solution or not, and if its solution is unique. And this is like one of the most, I mean, this is a problem of the importance of this problem is on the level of importance of Riemann hypothesis. So this is like about one of the most important problems which we have now. But in dimension 2D, Navier-Stokes equation is well posed and it's okay. So it's possible to study it, but still it's complicated. For example, for Navier-Stokes equation, which is perturbed by some noise, you should add the like white noise. Then it is proven that this process is mixing. So it's proven that there is a unique stationary state and that it has a convergence to the stationary state. Also, the noise actually can be very, very weak. You can shake only several first Fourier modes of your process and doesn't touch higher Fourier modes. This is sufficient. But this is very, very, very famous works, and it was done in the beginning of 2000s. Now it's still developing. Okay, so this is a big activity, and this is the simplest version of this large class of ergodic theorems, I would say. Because the Markov chains we consider are actually very, very simple. Okay, proof of the theorem. Proof. Let me maybe not just proof. Maybe I will I will separate two preliminary lemmas. Okay, so this will be lemma. I will use these lemmas in the proof. Lemma 22, which is the following simple, which affirms the following simple relation. Let us consider two arbitrary distributions. And let us consider the L1 difference. I mean, L1 norm of their difference. So L1 distance between them. Actually, this distance equals to the following. It equals to the sum over J from the set, which I will denote J large pi minus q. I will p minus q. I will introduce the set in several seconds. Pj minus qj, and I should also multiply this by 2. This set is defined as follows. For a vector v, I define the set JV as the set of all numbers of components such that the corresponding component is strictly positive. Okay. So I sum only over those J for which this difference is positive. Okay. The proof of this lemma is just one line. Proof. What is L1 norm of pi minus q? This is the sum of absolute values of components of this difference, right? So I can take the sum over J for which, okay, over this set, but I'll write down it explicitly now. So over J for which this difference is positive, pi j minus pj minus qj, and plus minus sum over J for which this difference is negative, pj minus qj, right? Because when you compute the absolute value, this is you should take the terms which are negative with sign minus, right? So you get exactly this. But we consider distributions. So the sum over all j of pj, this is the same as the sum over all j of qj, and this is just one. Just one, right? So it means that this sum should be equal to this sum. Okay. Let me maybe denote this by S1, by S plus, this by S minus. From here it follows that S minus equals to S plus. S minus equals to S plus. Because if I put instead of minus here plus, then I should get 0, because I will have the summation over all pj minus the summation over all qj. Except the terms where this difference equals to 0, but it's clear that there is no need to take it into account. So they're equal, and then I can replace this term by minus is minus. Okay. because this is negative. This is negative. They're equal, and that's why I can replace this term by the same term, and I get this factor 2. And this set is exactly JP minus Q. Is it clear? Okay. Perfect. So this is a very useful formula which I will employ. Lemma, and the next lemma is not significantly more complicated, but this is the K. This is the K of the proof. I'll maybe even give a name to this lemma. Let me call it contraction lemma. Yeah, actually, do you have any ideas how the ergodic theorem can be proved? I mean, how such kind of result can be obtained in principle? So what we wish to prove? We wish to prove that that what? That we wish to prove exponential ergodicity. So we wish to show that independently of the initial distribution, we have the convergence. But I think that you have already met such kind of results in real life, right? Where? How is it possible to get something like that?
Contracting.
Yes, exactly. So once you have map which is contracting, right, then you have fixed point, and you have exponential convergence to this fixed point. So the first idea, let us just try to find some contraction here. But where from this contraction may come? So where from this contraction may come? It turns out that this comes from the property of the transition probability matrix to be mixing. Let me formulate this. For any two distributions mu and nu, wait. Let Q be a matrix of size be a stochastic matrix of finite size, say L times L, for some L more than or equal to 1, satisfying. Not satisfying. Sorry, I just needed to be stochastic at the first part of my lemma. So this will be the first part. Then for any two distributions mu and nu, if I take the if I apply if I act on these distributions by the stochastic matrix Q, and then I consider the distance between the distributions after this action, then I see that the distance is not larger than the initial distance between these distributions. Okay. So I recall that stochastic matrix is a matrix such that all its elements are non-negative and sums over rows are equal to 1, so all transition between these matrices are always stochastics, and vice versa. Any stochastic matrix is a stochastic matrix of some Markov chain. The second point affirms that if there is number alpha positive such that all elements of the matrix are bounded from below by this alpha, so actually equivalently I say that all elements are strictly positive because my matrix is finite, right? Just alpha is the minimum of these elements. For any ij, then I have strong inequality. I should write here 1 minus alpha. So you see, and this is already. So this means that it is not expanding. Our map is not expanding, but this is already contraction in the space of distributions. So for any mu and nu from the space of distributions. So let me prove this lemma. How will we prove it? We'll just compute this difference, and that's it. Proof. So let us start with the first part. Let us just write down this distance. We have a nice formula to write it down. This is the formula that I've proven in the previous lemma. So this is the summation over J from. Let me abbreviate the set, which I should have here by JQ. So here JQ is just J mu Q minus nu Q. Okay, so this is a set of indices for which this difference is positive. Okay, so here I should write mu Q J minus mu Q J. Then I will write down this component. Yeah, I need to multiply by 2, right? But instead I will put here 1/2. Yeah, thank you. So I have, what do I have? I have summation from I over I from 1 to L. I recall that this is the size of the matrix. Mu I minus nu I over Q ij over Qij. Okay. Then now this is not less or equal than. This is just equal, right? So for the moment I had only identities. Now I wish to simplify it. I wish to bound it from above. How can I bound it? I can just throw away all negative terms from this sum, right? What does it mean? It means that I will take the summation not over all I, but only over those I for which this difference is the difference mu I minus nu I is positive. In other words, I will take the summation over the set j mu minus nu. And also I wish to exchange the order of two summations. In the result, I get summation over I from the set j mu minus nu, summation over indices j small from the set j large q, mu I minus mu I times q ij. Then look, this first term is independent from j, right? So I put it, I can put it here, and then I sum up over all j, right? So I get what? I get, but the sum over all j. This is bounded by 1, because the sum over the second index in stochastic matrix equals to 1. So this is bounded by sum over I from j. I think that it works worse than the previous time. This is backward. I mean, I have an impression that it is slower today. Mu I minus nu I. But what is this? What is this? This is exactly by our previous lemma. This is mu minus nu L1 norm 1/2. You see? So in the result, we get what we wish. We get that the norm after the action by Q is bounded by the initial norm. Questions? So the second item. The second item of the lemma assumes additionally that all elements are bounded from all elements of the matrix are bounded from below by alpha. Where can we use it in these inequalities? Clearly, we can use it. We can use it just here. Look, here I had I replaced by 1 the sum over. Okay, maybe it isn't. Did I do it right? Yellow. I replaced by 1 the sum over j from the set qij. Right? I've just written down that this is smaller than or equal to 1. What is 1? 1, this is the sum over all j. Over all j. But now we know that 1 qij, at least that all qij's are bounded from below. Also, let us note that this set cannot be equal to the set of all to the set of all possible states. Why is it so, actually? Do you understand? Why is it so? So just what is this set? The set is defined. It is defined like that. So this is a set where components of these guys of this difference are positive. right? Is it possible if we have an equality, if we have the equality here, then what? Then it means that for all components, mu q j is larger than mu q j, right? It means exactly this. But is it possible or not? What do we know about mu q and mu q? The mu and nu, they are distributions. But these matrices are stochastic, and I recall you your homework where you should have proven that once you multiply distribution by stochastic matrix, you get distribution. It means that sum over all j of components of these vectors is 1, right?
Yes.
But if these components are larger than this, that's impossible, right? So this implies this relation. Perfect. It means that summation, that this sum actually it can be bounded not only by 1, but it can be bounded by 1 minus alpha. Just because there is at least one j, which does not belong to this guy, and then since all these guys are bounded from below by alpha, we get the sum is less than or equal to 1 minus alpha. Okay? Is it okay? Well, and then we just make this estimate in yellow more accurate. We obtain that the norm we are interested in is bounded by from here, that it's bounded by 1 minus alpha times the same that we had here, j mu minus mu, mu I minus mu I. It follows from here. So, no, it doesn't work. And this is exactly 1 minus alpha times 1/2 mu minus nu L1 norm. So that's it. So we have proven the limit. Now let us prove our ergodic theorem. Proof of the theorem. Proof of the theorem. So we have already found some contraction when once we have a stochastic matrix, but who should play a role of this Q in our theorem? How do we see?
It is a transition probability matrix to the power of S.
Exactly, exactly. So we will use, because once we take the transition probability matrix to the power S, then all its components become non-negative, right? Strictly positive, sorry, strictly positive by assumption, because this matrix is assumed to be mixing. And then we will take this matrix for Q. And what does it mean? It means the following. So then actually once you have this lemma and once you have this idea, then I'm pretty sure that each of us will be able to write down this proof by yourself. Just the question is how to arrange it in a shortest way. I suggest to do the following. So let us divide the proof in several steps. Step 1, take arbitrary initial conditions. Let's call them arbitrary two initial distributions. Let's call them P0 and P0 tilde. And then let us consider the corresponding Pn and Pn tilde, which are obtained from these initial conditions along the dynamics of our Markov chain. And let us compute the L1 norm of difference between them. L1 distance between them. So, what is this? This is pi 0 transition probability matrix to the power n minus pi 0 tilde transition probability matrix to the power n L1 norm. Right? So then I can write it in the following form. I wish to go by S steps. This equals to pi n minus s. Maybe this formula even was so there is no need actually to write this down. I will keep it, but you can directly pass here actually. Maybe it's even simpler to think like that. N minus s pi to the power s pi large minus p tilde n minus s pi large to the power s L1 norm. L1 norm. This is less than or equal to what? By our lemma, it was, what was the number of the last lemma? 23. By lemma 23, this is bounded by 1 minus alpha, 1 minus alpha times the L1 norm of P n minus s minus P tilde n minus s L1 norm, where alpha this is just minimum over all ij of elements of the matrix, of the transition probability matrix taken to the power s. Then we continue we make S steps once, twice, etc. We make more and more steps. And how many steps can we make actually?
How
Yes.
Naturally.
Yeah, but we should also take the entire part, right?
Yeah.
N over S entire part. So this is the maximal number of steps I can make. Well, maybe I should write it more properly. This equals then 1 minus alpha to the power N over S entire part. Oh, sorry. Sorry, I will happen, okay? Hello? Okay. And now I have what? I have N minus S times N over S.
Probably M mod S.
Exactly. Thank you. Thank you. It's simply write N mod S. N mod S minus pi tilde N mod S L1 norm. But this is just this, so it equals then 2 times 1 minus alpha to this power N over S entire part. Right? So actually it remains to choose not remains, but the next thing that I wish to do, I wish to write it in a more accurate way. I wish to write it as constant C times lambda to the power n, but who is lambda then? Lambda then is who?
1 minus alpha in power.
One
Half
minus
of 1
alpha
divided by S.
to the power to the power 1 over S to the power 1 over S. Maybe 1. Let us think. Maybe I can write it 1 over. Okay, 1 over S. It's okay. 1 over S. It's okay. And then the constant C. This will be 2. This 2 times okay, I should write like that, less or equal then. I think like that, minus alpha to the power minus 1. Like that it should work, I think. 1 minus 1 over S. I agree with that. Look, because when I take this to the power n, I get n over s. Then when I multiply, this is less than 1, so the inequality will become, I get the number which is larger if I will make this power smaller. When I subtract 1 over s, I get the power which is smaller than this, so it's okay. Okay. So, just because what?
How did we remove the part with P and P tilde? How did we remove the L1 norm of...
This is triangle inequality. This is triangle inequality. Triangle inequality says that this difference, okay, for any two distributions, their difference L1 norm is less or equal than their sum, right? But the L1 norm of any distribution, this is 1. Okay? And then the area is between. So yes, this is correct.
Okay,
And
I
then
I just don't really understand why.
Why what?
N divided by S minus n minus 1 divided by S is less than the whole part of the n divided by S. But probably I'm not fast enough.
Okay, just to look. This computation is always complicated. It doesn't work anymore. Okay. Maybe we should just wait. Yes.
Oh, okay, yeah, it's okay.
It's okay, right?
It's okay.
Let me let's write it down. So n over s entire part is less than or equal, no, is bounded from below by n over s minus 1. N minus s, minus 1 over s, right? Like that. Or not? Wait.
Why do we even care about this? Wouldn't we take just a large enough C?
Yes, but I of course it works. But I wish to write the explicit code. I do not need this below, but I wish to do this. Okay, just okay. Let us look. This guy, that's for sure that the estimate
it
which
just
was
doesn't work for example, I don't know, n equals 5 and s equals 3.
wait. This is correct, right? This is for sure correct. Okay.
This one is good.
This is correct. So let us use this because before it was not correct, of course. Then what do we have? We have constant c. So it means that here I should have not 1 minus 1 over s, just minus 1. So the first thing that I written down, it was correct, right?
Yeah.
Okay. Yes. Thank you. Okay, anyway, we have some constant which becomes larger once alpha becomes closer and closer to 1. But this constant, it isn't, I mean, it's just constant which is already always the same, so no problems with this constant. What is important here is this lambda. And this lambda becomes worse and worse when alpha approaches to 1. Worse and worse in the sense that lambda becomes closer and closer to 1, and the rate of these conversions becomes slower and slower. So once alpha is large, what? So sorry. If alpha is small, then it is bad, right? If alpha is small, it is bad because this is almost 1. So if our matrix is ergodic but not so ergodic, so its elements approach to 0, then it is not good. But if these elements are separated from 0, for example, by 1/2, then we have very good estimates. Of course, which becomes worse and worse also depending on on S. If S is large, this guy also approaches to 1. Okay? So the best convergence is achieved once all elements are well separated from 0 and S equals to 1. Okay. So, but this what have we already proved? We proved the let me maybe write it down. explicitly. We have proven that pi n minus pi tilde n, these are two distributions corresponding to different initial conditions. They are bounded by c to the lambda to the power n. That's what we have proven for the moment. Now we need to prove that Pn converges to the stationary state. So just how one can do this? Just take.
Sorry, do we even need this convergence?
Hmm?
We already know that if we take arbitrary initial state, Pn and Pn tilde, we have this relation.
Yes.
Also, we know that Markov chain with finite number of states
Yes.
admits stationary measure.
Yes.
So take P tilde 0 equals to pi.
Yes. This is a possible way. This is a possible very good way,
But Pn does not need to converge to
yes,
pi.
but just I don't want to refer to this previous result because
Okay.
I mean, it isn't needed here. I can write down just one line plus, but without using this previous result about the existence of the Markov chain. Okay. It follows that if I maybe yes, I used to slightly so I'm sorry, I used to slightly change this result. Look, I will do the following. I will not write down here the same n. I will take n and m will be larger, and here I will take m instead of n. Okay. Then here I will have m. Here I will have m. Here I will have m. Here I will also have m. And here it is the same. Here I have not m mod s, but here I have some power like m minus n over s entire part. But it isn't important because this guy is anyway bounded by 2, right? By 2. So nothing changes. And if n is smaller, or equals than n. Very good. And here it is convenient because I can just take pi 0 equal to pi. This is just for free. You see, I can take pi 0 equal to pi 0 tilde. Well, 0. I have 0 above. Pi 0 tilde. For and then I'll get just that this sequence is fundamental. The sequence phi n is fundamental. Okay. Fundamental in L1 norm, right? Then it converges. Let us call it limit. It's a limit by pi. For the moment, pi. This is just some distribution.
It's not even a distribution. distribution.
It's distribution.
It is distribution, but it is a proposition that pi is a distribution because L1 is complete.
Yes, yes,
the
yes.
space
Yes,
of
but yes, yes.
all
But we
sequences.
already discussed the space of measures. This is a simplex.
Ah, okay, okay, yes, yes, it's closed subset. Yes.
It's closed. It's compact subset. Then let us show that pi is a stationary distribution. Is a stationary distribution. To this end, we need just to write down pi minus pi times p. This equals to this L1 difference, and we need to show that it is 0. We can write it as limit when n goes to infinity of pi minus some say pi n p, right? Because of the continuity of all operations which are inside of this limit, right? And then this thing, this is just Pn plus 1, and it also converges to pi. This equals to pi minus pi, which is 0. Right, so pi is stationary. And the last thing we need to prove, let me maybe call it step 3, that pi is a unique stationary measure. Because for the moment we have proven that pi is some stationary measure. Let us show that pi is a unique, is the unique maybe stationary measure. So let pi tilde be another stationary measure. Okay, so now we haven't proven yet. So look, we have proven that arbitrary sequence of this form converges to some stationary measure, right? To some stationary measure. Then if we show that all stationary measures coincide, then it will be okay. It will mean that every sequence like that converges to the same stationary measure, right? Exactly what we want. So indeed, we need to show that the stationary measure is unique. So let us show this. Let us take another stationary measure, and then let us consider the sequence. Let us consider the following object. Let us consider the difference, of course, between pi and pi tilde. This equals to what? To pi. Since they are stationary, I can write like that: pi tilde times pi times transition probability matrix to the power n minus pi, then transition probability matrix to the power n, right? Because they are stationary. but this is less than or equal to lambda to the power c lambda to the power n, right? Because of this inequality. With pi 0 and pi 0 tilde equal to, with p0 and p0 tilde equal to pi tilde and pi less than or equal to c lambda to the power n goes to 0. So the theorem, so now we have proven that everything falls down on the same stationary measure. So we have proven the main assertion of the theorem. But there was another one assertion. There was an assertion that all components of the stationary measure are strictly positive. So let me prove this. Let me prove this as well. So step 4. Let us show that pi j, they are strictly positive for all j. How can we prove this? We can write what is pi j. Pi j, this is just what? Since pi is a stationary measure, this is pi times p times pi large, the transition probability matrix, the component number j. But this is the sum of over all I of pi I times transition probability matrix component number ij, but what all these guys, they're more than or equal to alpha, right? No, to the power s. Let us take it to the power s. Okay. To the power s, component number ij. Now that's correct. Then this is more than or equal to alpha times sum of the components of the vector pi, which is alpha. So the theorem is proven. Let me mention corollary. Do you have any questions about proof? So corollary 24. Assume, okay, under assumptions, the assumptions of the theorem of the ergodic theorem the transition probability matrix to the power n converges to the following matrix. Pi 1, pi l. So all lines of this matrix are of all rows of this matrix are the same. They just consist of the vector pi, which is the stationary distribution. So I will write it shorter like that. goes to infinity. You see, so under the limit, transition probability matrix takes a very simple form. What actually does it mean? It means the following. What is the transition probability matrix to the power n? This is the transition probability matrix of the Markov chain in n steps, right? If you wish to look, where do you arrive? When you look not at every step, but you make n steps, then n steps, then n steps, and so on. So when n goes to infinity, it affirms that the transition probabilities of this Markov chain will be just stationary probabilities of the corresponding state. That is, what is the element with components ij of this matrix. This is the probability to start with at the state I, and then to go to arrive in n steps to the state j in n steps, right? And it turns out that this probability converges to what? It is independent from I, it depends only on j, and it converges to pi j.
So this is a pointwise convergence, not pointwise, but element-wise.
All convergences are equivalent in finite dimension, so
Okay.
you can choose the convergence you prefer and use it. Yeah. So actually, the convergence here is exponential, of course, right? It immediately follows from the theorem.
Mm-hmm.
Okay. So I'll prove it this corollary now, and you will see this. So it means that the probability to arrive at the state j in large number of steps is independent from the state where you start, and it approximately equals to the stationary probability of the state j. The proof of the corollary is just very simple. What do we need? We need to obtain components of this matrix pi to the power n, and to this end I will choose special initial distribution. The special initial distribution of the following form. So let me take zeros everywhere. Then at the position number I will take 1, and then all the remaining positions will be occupied by 0. And then if I compute the corresponding distribution at the moment of time n, which equals to this initial distribution multiplied by the transition probability matrix to the power n. What is this? This is exactly what? This is the row. This is the row number I of this matrix, right? This is the row number I. Okay? And our theorem says that this pi n converges to pi when n goes to infinity. Right? So it means that this row converges to the stationary distribution. This is exactly what I want. So in particular, this convergence is exponential. So it's time to stop. Concerning the future, we have counter work on 11th of November, 11th, right? The next time this is the holiday. But I will do the following. I will try to do this maybe today or tomorrow. I will put the new set of problems. This will be the last set of problems before the control war. And then I suggest you, I will write down this to the chat in Telegram. I will suggest you to vote for problems which you want to discuss. And instead of the next lecture, I will either write down solutions of some problems, or maybe this is more probable. I will just make some oral discussion of these problems. So I think that I will be able to discuss like about 3 problems, because I don't want, in particular, I don't want to solve all the problems instead of you. That's why I'm always ready to discuss your questions, but to give complete solutions, I will give complete solutions maybe to 3 selected problems, which you select by yourself, and we'll organize some selections of these problems in the Telegram, right? Okay. And the deadline I think will be, I will think about the deadline to choose this problem to discuss will be, I think, the next Thursday. Okay.
Последнее же это просто следствие эргодичности, правильно? Последнее утверждение это следствие, которое это же просто из эргодичности, а не из экспоненциальной эргодичности.
Да, конечно, из эргодичности. Но я не написал, что если хотим с экспоненциальной, мы появилось. Вообще-то экспоненциальная эргодичность. Там тоже нам на минус же.
Не. Я вот тут я поняла, почему я что я могла быть следующий февраль, что...
Так сумма всех и сейчас.
Которые не обязательно...
Сейчас.
Я не все, я уже... Да, все.
Короче, просто вы не помните ответ, какой примерно задача, где там, в общем, станция метро по центру,
Да.
и там как цветочек
Нет,
такой.
не помню.
Там отражение самое последнее, просто я не знаю, вот это нужно сворачивать или не нужно? Ну, собственно, я так на скидку не могу сказать.
Сейчас, а там что нужно было? Я уже забыл. Нужно посчитать.
Значит, вот мы в центре стоим, куда-то едем с равными вероятностями. Тау М это, значит, у нас М центральной станции есть, М еще дополнительных. Тау М это минимальный момент, когда мы все посетим.
Это минимальный момент, когда мы
все посетим, да.
Когда мы все посетим. Вот это посчитайте.
Я просто вот расписываю распределение такое.
Сейчас, пам-пам-пам. Значит, как вы вот эти вероятности считаете?
Ну вот у нас, когда есть М станций, и строка длины К есть. В самом конце, в самом последнем должна быть, а тут К минус одна станция, точнее К минус 1 это длина строки, и М минус 1 это алфавит. Я просто такую задачу решаю. Алфавит М, длина М, сколько строк, в которых есть все буквы.
Сколько строк, которых?
Ну, это включение-исключение.
Все буквы. Так, сейчас там включение. Сейчас там включение что-то немножко странно, потому что. Сейчас. Там. Сейчас. Сколько строк, в которых есть все буквы. Ну там как-то. Да, сейчас там.
Ну да, все обязательно. Ну, то есть я так расквалифицирую.
Сейчас. Так.
Вообще нет, сейчас. Это не от меня вообще зависит. Там все вот M-1. Если мы хотим, чтобы последний был самый последний момент, значит, что это M-1 должно быть все.
Может быть, то есть вы даже никакую цепь не рисуете, да?
Ну, цепь вот, она такая, конечно.
Да.
Вот. Но тут-то она мне не нужна, это другое вообще немножко. Это не совсем про эту же цепь. Ну, то есть это как бы связанные вещи. Вот. Это...
Сейчас. Сейчас, то есть действительно у вас есть некоторый алфавит, вам нужно посмотреть, значит, да, по-моему, это правильно. Я думаю, что
просто я не знаю, сворачивать.
Нет, я думаю, что нет, думаю, что не должны. Я просто не помню ответ. Но я посмотрю, давайте по умолчанию считать, что не сворачивается, а если сворачивается, Так, да, идем смотреть, спросить, что я долго не отвечал, значит, долго вопрос. Короче, ну, история такая, что, смотрите, у меня, значит, касательно, во-первых, того, какой там уровень строгости должен быть, но вот там статьи уже есть журнал, тогда значит, этого достаточно. Другое дело,
Сейчас не совсем понятно, чего
достаточно, я имею в виду, что ну, я так полистал, естественно, я там не вникал в детали, это нужно, чтобы мы просто рассказывали, значит, но с точки зрения уровня математики, я думаю, что это там для магистерской работы достаточно. Конечно, будет хорошо, если вы сможете задавать вопросы, а что это все-таки с математической точки зрения значит. Это хорошо. Вот. Но это не есть обязательная история. То есть, в принципе, люди разным занимаются в магистратуре, кто-то там какой-то экономикой занимается, кто-то там какими-то сетями. То есть, в общем, это, скажем так, доказывать теорему не обязательно. Вот. Но если она есть, то, конечно, хорошо. То есть проблем с этим, ну, нигде не прописано, значит, как должна выглядеть с точки зрения математики магистерская работа, но вроде бы проблем с этим не может быть. То есть я на самом деле про это сам, у меня не было ответа, я поговорил с Клименко, который меня отфутболил к Побережному, вот Побережный вот сказал то, что я вам сейчас транслирую. Вот. Значит, касательно руководства, смотрите, значит, мне кажется, что две полноценные задачи это сложно, по крайней мере, сразу это не то, что нужно делать, с одной стороны.
Нет, мне сейчас не сказать, чтобы есть какая-то прям вот активная деятельность, которой я занимаюсь, там, ну, следующая какая-то вот глобальная сподвижка, которую нужно осуществить, она где-то будет уже к весне, там, к апрелю, к маю, поэтому сейчас я не сказать, чтобы она...
Что значит глобальная сподвижка? Почему сейчас не надо осуществлять?
Там сейчас вот пока что единственное вот направление, в котором, ну, понятно, как совершить продвижение, заключается в том, что нужно вот посчитать там, ну, некоторое большое количество интегралов. То есть понятно, как считать, но по аналогу с тем, как там считались эти вклады и диаграммы для трехточника вероятности контакта, ну, вот, можно проделать как бы вот аналогичные вычисления для четырехточных вероятности контакта. Но это просто нужно вот...
Я трансляцию остановил, не расслушаю.
Да, и ну вот единственное как бы ну, вот направление, в котором сейчас понятно, как двигаться, это просто ну вот сесть, потратить там несколько дней, посчитать эти интегралы, ну и в общем... Да, и ну вот единственное как бы ну, вот направление, в котором сейчас понятно, как двигаться, это просто ну вот сесть, потратить там несколько